All right, so let's take a look at our lesson for today. It is the first lesson in a very exciting unit on integration. I know, it's so awesome. So we're going to talk about antidifferentiation. So in order to kind of lead us there, I want to talk about some processes like multiplication and division. Let's think about when we first learned multiplication, in elementary school. I mean, the times tables were kind of hard, but once you got it down, not a problem, right? Multiplying is pretty straightforward. But then when you learn to divide, it's like, oh, that's a little bit different. It's kind of backwards. It's kind of weird. And one of them undoes the other. Like if I multiply 2 times 3 and get 6, and then I divide 6 by 3, it puts me back to 2, right? So they basically will undo each other. If you do one and then the other, you'll get back to where you started. And the same thing with squaring something and square rooting it, right? If you square, 2 and get 4, then you square root it, you go back to 2. So they undo. They're processes that undo each other. That's the exact same thing with differentiation and antidifferentiation. Those processes undo each other, if we would want to think of it that way. The differentiation process is more basically related to multiplication. It's the first thing that you learned, and you can take the derivative of anything. Anything. By now, you know how to take the derivative of anything. The reverse is not true, though. The integration, or the antidifferentiation, is kind of like dividing. It's really kind of particular. It's a little bit more difficult. Or like factoring, multiplying and factoring. Factoring was hard, right? So antidifferentiation is just a little bit more difficult because it has to be exactly in such a way. We thought we didn't have, a ton of rules in derivatives. We've got an extra ton in antidifferentiation. So let's look at it. First of all, let's talk about the concept itself. The process of taking antiderivatives is called integration. It's basically kind of the same thing. The process of taking antiderivatives is called integration. And we're going to start with specifically, where are we? So we're going to start with the indefinite integration. So what does that mean? That means that there aren't any numbers on this integral sign. Definite integration would have numbers here. We start out with indefinite integration. There are no numbers. We'll get to numbers, but that's later. And we also have to use the constant integration C. We'll talk about that, constant of integration C. We're going to talk about that quite a bit. So we use a symbol to represent the antiderivative. It's called an integral sign, this little S-looking thing. You've probably seen it before. And the integral is written like this, integral f of x dx. So I want to spend a little bit of time on this dx. In Calculus 1 and Calculus 2, this dx seems like extra. We wonder why are we putting it. Well, what it does is it tells us which variable we are integrating with respect to. When we go into Calculus 3, multivariable calculus, these become, necessary, critical, because we have more than one variable that we're integrating, and we have to do it in the specific order that it lists it. So for us in Cal 1 and Cal 2, a lot of students just forget to write it. It's really important that you do write it, because basically what it does is it kind of binds in this part. It's called the integrand. See how I have an integral sign, and then I have the integrand, and then it ends it with the dx? So if I forget to put this dx, then how do I know where I'm ending? Right? So it's really kind of the end to your problem. Now, typical, you don't have to, it doesn't have to be, I'm just talking about the typical way that you would write it. If I integrated like f of x, the antiderivative is usually written with a capital F. Do you have to? No. That's just kind of a way, a pattern that you will see. That if I integrate like little f, then we get big F of x plus c. Let's see. So when we were doing limits, remember that? We had so many rules we could use. It was like a ton of them. Remember that? You could split the limit. You could have the limit divided by another limit. We got to do all kind of things. With antidifferentiation or integration, we only have 2. We have 2 rules. That's it. We can add and subtract things. We can split it by adding and subtracting. which is kind of nice. You know, basically if we're integrating like a polynomial, we can do the antiderivative of each individual term, you know, separated by plus minus. That's great. That's fine. And there's just one other thing we can do. We can pull a constant outside of the integral sign, take the antiderivative, then put it back. Kind of a little bit like derivatives, a little bit, where we pull the, you know, the constant out and then put it back. That's it. It's really important for you to recognize this is does not equal, and it may not show up very well on the copy that you made, but it does not equal. If you're multiplying, that you're integrating f of x times g of x, you cannot integrate those, you know, the integral of f of x dx times integral of f of g of x. Just can't do it. That is not okay. And it is not okay to do that with a quotient either. Not okay. All right. So you're looking at the rules. You're probably like, oh, this is so exciting. Look at how many more formula quizzes we can have. Right? How many more different versions? But really, I will tell you, I'm old, right? I've been doing this a long time. I don't go through and memorize all of these. I don't have them memorized. What I have memorized are the derivatives. That's what I have memorized. I don't want to try to memorize both sides because to me it's too confusing. It's just way confusing for me to memorize both sides. Instead, this is what I do when I'm working an integral problem. I'll look at this and I'll say, okay, what would I have taken the derivative of to have gotten a positive cosine? That's what I would ask myself every single time. What would I have taken the derivative of to get a positive cosine? I would have taken the derivative of sine, right? And that's what we did. So sine x plus c. That's how I do it. I don't memorize a whole nother set of formulas. Now, if you don't like that, if you don't want to think about it that way, then please, by all means, memorize that whole other set of formulas, and that will be fine. So really you have one or the other choice, right? You can think about it as what would I have taken the derivative of to have gotten this, or you can memorize that whole other set of formulas. So let's just kind of take a look at some of the formulas. This, we'll look at this one, is basically our power rule reversed. It's like a reversal power rule. I want you to study it for just a moment. Notice how if I'm integrating like x squared or something, what this reversal power rule has me do, it just does the opposite. Instead of subtracting 1 from my exponent, I'm going to add 1. And instead of multiplying by the exponent, I'm going to divide by the new one. That's the reversal power rule, and we're going to get a lot of practice on that today. Let's see another one. Another one that I want to point out is this one. Okay, and I've been pointing it out all day, and students are still confused by it. All right, the integral of 1 over x. So you ask yourself, what would I have taken the derivative of to have gotten a 1 over x as my derivative? I would have taken the derivative of natural log x, right? Derivative of natural log x is 1 over x. The only little nuance here is these have to have this absolute value. That's kind of not from the derivative, it's from the integral. They have to be. So the integral of 1 over x dx is natural log absolute value of x plus c. All right, so now let's talk about the plus c. We keep seeing plus c, plus c. Well, what's the deal with that? Well, let's look, I'm just going to give you a couple of examples. Let's say we have a function, it's 3x squared plus 5. All right, let's take the derivative of it. So f prime of x is 6x. Okay, that's okay. Let's say we have another function, and this function is 3x squared minus 74. Okay, I'm going to take the derivative of it. G prime of x is 6x. Are we seeing any problems with that? They have the same derivative. They're not the same equation at all, are they? Not at all. In fact, if I go backwards and I integrate this, I'm going to get 3x squared, but who knows what I would get there? That's where the plus c comes in. Okay, so let's just pretend. Let's pretend that we don't know what these positions are. Let's just integrate. We're going to integrate this f prime of x. We're going to go backwards. So f of x would be, so we use our reversal power rule. I'm going to add 1 to the exponent. Right now the exponent is 1, so 1 plus 1 is 2. Then I'm going to divide by 2. So it's going to be 6 over 2. Okay, of course, plus c. So that would be 3x squared. If I didn't put the plus C, well, how would I know, what about this? How do we know what this was? So I'm hoping with that you can see why we have to put a plus C. Now, I will tell you, I give a point for the C's. And so some of my students will, at the end of the year, will say, oh my gosh, I lost 32 points this year because of plus C. I mean, they counted it up on all their quizzes, all their tests, everything. 32 points for forgetting to put plus C. Sometimes students will even put on the top of the paper a big, like gigantic, plus C, like 4 inches big on top of the paper, and they will still forget to put plus C. All right, so I'm just telling you, you have to put plus C, and I hope you understand why. It's because of this scenario right here. If you don't put plus C, what are you saying C is? 0. And we don't know that, right? We don't know that unless we're given additional information. So I'm just giving you the heads up. Plus C is a big deal. All right, so let's go work a couple of examples. By the way, before I get off this formula page, I need to be very, very clear. If the integral doesn't look exactly like this, let's say it was cosine 2x. Can't do it, okay, until we learn something else, which we actually will learn tomorrow, use substitution. But it has to look exactly like this to use this rule, okay? If it's anything different at all, you have to use another rule. Are you with me? So it has to be like cosine x, sine x, just exactly how these look. No numbers in there, nothing else going on. So that's what we're dealing with today, just some pretty much straight antidifferentiation. All right, so let's do a couple of examples. So the first one, I guess it's kind of hard to see. That won't move anymore. So that's the integral of 2x minus 1 times x plus 3. Right off the bat, we have something that some students might try to make up a rule to do. All right, do we have a rule that looks like that? No. We have to FOIL it out. Even when we learn rules that will allow us to multiply things, we're really going to want to just FOIL this out. I promise. We just really want to FOIL it out. So let's do that. So we're just going to FOIL that out, and we're going to get 2x squared plus 5x minus 3. Okay, again, the dx is there, is holding the integrand in. If you want to, you can make it more specific by putting parentheses here. That's fine. It's more clear. But if you always remember to put the dx, you really don't need to worry about the parentheses because it's the end of the integral statement. All right, so now let's integrate. So we have here, it's a 2, so we're going to add 1 to 2. So that gives me x cubed, and then I'm going to divide by 3. So 2/3 plus. Okay, here I'm going to add 1. There's an exponent of 1 here. I'm going to add 1 to 1 and get 2. Then I'm going to divide by 2. Minus 3x plus c. Now, if you're ever worried, and I know sometimes it can be a little alarming that going backwards like this, if you're ever worried that you've done it incorrectly, all you have to do is just do the derivative here and see if you get back to where you started. So if I bring a 3 down, don't I get 2 and then subtract 1? See, so you can just double check yourself that way if it's ever a problem. Just do the derivative and see if you get back. And there we go. It's our very first one. Notice I don't have f of x equals, I don't have anything like that because I wasn't given any information on the name. So it's just an expression. And we put plus c. Okay? On the next one, it says solve the differential equation. Now, those are math words that you have to know what they mean. I'm introducing them now because I'll tell you right now you're going to understand what I'm saying, but in a week or two when I put this on a quiz or a test, there will be students that won't even know what to do when you have this instruction. So it's really important. It's a vocabulary word. What is a differential equation? It's an equation that has a derivative. That's a differential equation. An equation that has a derivative. What does it mean to solve a differential equation? To solve a differential equation, it means that you are finding the position function. You're finding the position. You have the differential equation, you're going to go backwards and find the position. That's what it means. So it's kind of code words. If you don't know what it means, you'll just stare at the problem and are like, I don't know what to do. Okay, so now we know what to do. So we're actually asked to find the position, and this is a second derivative. Are we going to be able to do that in one step? Just jump back to the position? No, we're going to have to go through the first derivative, then back to the position. And in this case, notice this extra information that we have right here. That extra information is there so that we will be able to find out what C is. That's what it's there for. We didn't have any additional information over here. We don't know what C is. This is called a general antiderivative. The word general is used because it actually represents like a family of antiderivatives. So this is the general antiderivative. Over here, we're going to be finding specific ones because we have this additional information. So let's start. So we know that we need to go to f prime. And f prime is going to be the integral of cosine of x dx. That's what f prime is, right? Because I'm going backwards one. All right, so we think to ourselves, what would we have taken the derivative of to have gotten a cosine, a positive cosine? It would have been a positive sine, right? So this would be sine x plus c. Now, we need to find out what c is. Some of you can do it in your head. I'm going to write it out. I'll just write it out. So we have this piece of information right here. So when x is 0, y is 3. So 3 equals sine of 0 plus c. So we know sine of 0 is 0, and so c equals 3. So I know that f prime of x is sine x plus 3. Okay, we okay so far? Mm-hmm. So it would have to be more specific. You wouldn't take an implication. So here I'm using c for the first derivative, and actually I'm going to use c again for the position, and that really troubled some students earlier. If that troubles you, please don't do that. The reason that I use c over and over again is that's just the traditional thing that we call the constant. Knowing that just because this is c does not mean that this is going to apply to the next integral that I do. Okay, we need to be clear on that. If that is going to trouble you, if this not changing the variable troubles you, then please change the variable every time, because it really is just the constant of integration. It's not really, this doesn't mean that c is 3 all the time. That's not what this means. It just means that in this case, for this integral alone, c is 3. That's all that means. Okay, so let's find our next one. We're going to find the position. So f of x is going to be the integral of f prime, and f prime is sine x plus 3 dx. Okay, so here we go. So let's think. What would we have taken the derivative of to have gotten a positive sine? That would have to be a negative cosine, wouldn't it? Because it would have to be negative. So negative cosine x plus, and then the 3, the integral of 3 is 3x. Plus c. Again, I'm using c just because that's the traditional constant. It doesn't mean it's this c, it's just another c. Some textbooks do like c sub 1, c sub 2. Maybe you want to do that if that troubles you. You certainly can do that. You don't have to, but if it troubles you, please sub number them like 1, 2. Alright, so now let's see. We have this piece of information to find out what this particular constant of integration is. So let's do that. So our y value is negative 2. Negative 2 equals negative cosine x plus 3x. Oops, x is 0. So let's go ahead at the same time. Let's put our 0 in there. So cosine of 0 plus 3 times 0 plus c. And we'll just say c2. All right. So now we work that all out. We know cosine of 0 is 1. So that's a negative 2 equals negative 1 plus c. So c is negative 1. So my solution to my differential equation is negative cosine x plus 3x minus 1. And that is my solution to my differential equation. That is a specific solution. Sometimes they want a general solution. A general solution would mean that we would still have c here. C or d or however many times we've had to integrate. Okay? All right, let's go to the next example. So we have a particle moving along the x-axis at a velocity of, and we have a velocity equation. At time t equals 2, its position is x equals 3. Okay, so let's hold there for a minute. That's a little confusing. So our independent variable is t, right? This would be like our x. It's like they're giving us the x value here. Our dependent variable, they're calling it x, and that's because there's really two kind of main ways to call a position function. One is s of t, the other is x of t. Both are normally used for position, and they're using x of t, which I know can be very confusing. But this x value is really not the x value. This would be like the y value. Okay, so let's just make note of that. We're given a position value. All right, part A, find the acceleration. Oh, what does that mean? We're going to have to do a derivative, right? So from now on, you're going to have to be going back and forth all the time. You have to keep them straight. Am I doing a derivative? Am I doing an integral? Which way am I going? So there we go. Opens up more fun. So a of t equals, so let's do the derivative of this velocity. So that would be 12t squared minus 6t. Okay, not bad, right? We like derivatives. All right, so now we want to find the position. Okay, so to find the position, am I going to integrate the acceleration or am I going to integrate the velocity? The velocity, right? I need to go back one from velocity. So x of t, because that's what they're using as the variable, x of t equals the integral of 4t cubed minus 3t squared plus 5 dt. Notice I put dt here because that's the variable that we're using. It's still a single variable. We're not doing multiple variables, but it's t instead of x, so I put dt. All right, so now let's integrate. So x of t equals, so I'm going to add 1 to the 3, right? That gives me a 4. I'm going to divide by 4. So that gives me t to the 4th minus, I'm going to add 1 to the 2, which is 3, divide by 3, t cubed plus 5t plus c. All right, again, if you're ever worried you've done your reversal power rule wrong, just do the derivative, make sure you get what you came from. Now our job is to find c, so we're going to go back to this information. So 3 equals 2 to the 4th minus 2 cubed plus 5 times 2 plus c. Now just to save you all the arithmetic, c turns out to be negative 15. So my x of t is, so we have what? We have t to the 4th minus t cubed plus 5t minus 15. Okay, how are we? Okay? All right, last one. We have the second derivative and we're asked to find f. We don't have any additional information here, do we? So it's going to have to stay general. It's going to be general. I'm not going to be able to find c. All right, so let's find f prime. So f prime is going to be the integral of 1 plus x to the 4/5 dx. Okay? So let's do that. So that equals, so the integral of 1 is x. Okay, fractions are a little bit different, so let's kind of walk through this. The integral of x to the 4/5. So I add 1 to 4/5, and I get 9/5. Okay? Then I divide by 9/5. Dividing by 9/5 is the same thing as multiplying by 5/9, right? So this is multiplied by 5/9, and then plus c. Okay, how are we? Okay? So now I'm going to integrate, I'm going to go back to f. So f of x equals integral of x plus 5/9 x to the 9/5 plus c dx. Okay, dx is like the end of my integral problem. Okay, so now let's integrate. So f of x is going to be, the integral of x is 1/2 x squared. So I did the reversal power rule. hopefully this will come to you and it's okay. Are we all right with that? 1/2 x squared. Then this next one is a fraction little issue. I'm actually going to write down the 5/9. You know, I just don't want to try to do the fractions in my head. I'm just going to write down the 5/9, kind of leave it there for a second, and I'm going to deal with x to the 9/5. All right, so if I add 1 to 9/5, I get 14/5, right? So x to the 14/5. Then I have to divide by 14/5. Dividing by 14/5 is the same thing as multiplying by 5/14, right? So I'm going to multiply by 5/14. And I'm just going to have to clean it up in a minute. In just a moment, I'm going to have to multiply all that. Let's keep going, though. The integral of c. So c is just some number, right? We don't know what it is, but it's some number. So the integral of c would be cx. And since I've already used c, I can't use it again unless I do the subnumbering. I could do that. But I'm just going to do a little bit different so you can see different ways. I'm going to say plus d. Okay, so let's do one more step where we clean it up. So I have 1/2 x squared plus 25 over, let's see, 9 times 14 is 126. X to the 14/5 plus cx plus d. Okay, how are we? And that is a 6. All right? All right, great.